Now, I'm sure you'll remember this. We've got a battery with the positive terminal at the top, negative terminal at the bottom, feeding current through a resistor. The current will flow in the direction shown here, going from left to right. Conventional current flowing from positive to negative. So, how would we go about measuring that voltage? Well, you'd measure it with a test meter. The test meter has a couple of probes. First problem then is, how do you set the test meter and where do you connect the probes? Well, we know that the voltage across this resistor is going to be DC and there's little chance of it being more than 20 volts. So let's switch the meter to the 20 volt DC range. Then it comes to where do you connect the probes? Well, the black probe is the reference point. In any circuit, you need to have a reference, somewhere to stand, if you like, to look at the other voltages in the circuit. Well, our reference point is generally the negative side of the supply. So we'll connect the black terminal to the negative side of the battery. So the only place left to connect the red probe to is the positive side of the battery. As soon as you connect it up, you'll see the display on the meter change to the voltage. In this case, 3 volts. Now that's because this just happens to be a 3 volt battery. If it was a 6 volt battery, it would be 6 volts. Or thereabouts. Don't worry too much if the voltage isn't exactly what you expect. If we were to connect this to a power supply, then we would expect to see 12 volts out of that power supply. You might well find that your meter reads 14 volts. That's because the power supply is running without any load on it. It's not doing a great deal of work. As soon as you connect it to a circuit, that voltage would drop to round about 12. So don't be too worried about that voltage. It doesn't have to be specifically what you're looking for. If you connected the meter across the resistor and you were getting no volts, yet you knew you had a 12 volt battery in there, that's the time to worry. You've either got a flat battery or something in the circuit is broken. So that's how we would check the voltage with a test meter. We could also show that voltage in the form of a graph. So again, using those same 2 points, the voltage across the battery or the resistor, they're both the same. The voltage has got to be somewhere between 0 and 20 volts. If you connect it across 12 volts, the graph would look like that. If you connected it across 3 volts, it would look like that. And 6 volts, like that. Now we've shown time as the horizontal axis there. For DC, time really doesn't make any difference. I suppose if you left the circuit connected up long enough and the battery went flat, then you'd see that voltage gradually fall. But normally, for normal use, it's just a straight line. So that's how we'd look at and represent a DC voltage. Let's now have a look at AC. Now AC, as its name says, has alternating current. The current, rather than like DC, always in the same direction, AC alternates. Let's see how that works. First of all, you'll notice our axis has changed a bit. We've now got plus 20 and minus 20 volts on there. And certainly now, the timeline is going to be important. We'll start off, as AC does, at no volts at all coming into the circuit. And slowly the voltage rises. So the voltage is in just the same direction it was with DC. The current is in the same direction as it was with DC. And it rises from 0 up to, looks like about 14, 15 volts on this graph. And then it drops down to 0. Great. So at this moment in time, we've got no voltage across the resistor, no voltage coming into the circuit, no current flowing, nothing. But next, we want to make the current alternate. So whereas before we had the positive terminal on the top, that's now going to go negative. And the negative terminal on the bottom goes positive. That forces current the other way through the circuit. The current rises and then falls to zero. That is called one cycle of AC. In the UK, our mains voltage is doing that 50 times a second, going up to a peak, not, I hasten to add, of 14 volts, but significantly more than that and very dangerously more than that, dropping to zero, going negative by the same amount, and then dropping up to zero again. So it's going at 50 times a second, 50 cycles a second, or 50 hertz. So that's going along at a nice lick. Now you might say, what on earth is the point of all that? And I would have to say, absolutely none at all across a resistor. What is interesting though, is if we replace the resistor with a transformer. Now somewhere between the main socket and your train controller will be a transformer. It might be in that little box you plug into the wall, or it might be a larger unit that mounts on the baseboard. But the transformer will have 240 volts mains going in. Again, let's stress, please do not meddle with the mains. It is extremely dangerous. The transformer is made up of a number of coils of wire. This one's got two, a primary winding, which is the one that takes the mains input, and a secondary winding. If there are as many turns on the primary winding as on the secondary, then with 240 volts AC going in, you get 240 volts AC out. Now again, you might say, what's the point of that? There are some benefits of doing that, but we needn't go into that right now. The really interesting thing is, if there are fewer turns on the secondary, we don't get so many volts out. So we can use this transformer to take 240 volt mains in and get 12 volts AC out. This is a much more suitable voltage for us to use. Transformer manufacturers can add many more windings, so let's use one with an extra winding with a few more turns and get 16 volts AC out of it. Now 16 volts you'll probably recognise as the AC out of some of the larger power supplies that you see for model railways. This is an ideal source of current for driving lights, point motors, etc. But the AC voltage, 12 volts or 16 volts, is not good for driving locomotives. No matter whether you're using DC or DCC systems, the motor in the locomotive is a DC motor. If you were to put an AC voltage across a motor, the motor would just overheat and the whole thing would go up in smoke. What we can do with that 12 volt AC supply though is convert it to DC for feeding the controller. Now whether it's a DC controller system or a DCC controller system, it still needs DC to operate. So we can take the 12 volts AC and feed it to an AC to DC converter circuit. That will give us a nice stable DC supply which we can then feed into our train controller to control the speed.